Well, ladies and gentlemen, a very good morning. Good morning to you all, and once again, welcome to the Royal Court Theatre for another presentation in our 2018 World Space Week. And I know a lot of you do have questions, so what we're going to do tomorrow at 11 o'clock in here, all our keynote speakers from our Space Week will be on stage with me as a panel, and we'll have an open question and answer session with all of you. So that will take place tomorrow, and it'll be a pleasure to host that. Ladies and gentlemen, it's my great pleasure now to welcome back to the Royal Court Theatre stage. Please welcome our keynote speaker, Dr. Lawrence Kuznets.
Thank you, Paul. Thank you. Morning, everyone. Today's a really interesting talk. I know somewhere out in the audience, whenever a scientist gets up in front of a stage and starts blabbing on about science and the planets or medical breakthroughs or the latest in bridge building or astronomy, somebody out there is thinking, I wonder what that person thinks about God. And that is really a difficult topic for a lot of scientists to bridge, because we don't usually go there, and not that we don't believe in the higher spirit, but it's kind of not in our purview, our normal purview, So I thought I would take a chance and try to think about this in a scientific way, and that's what today's talk is about. So I hope I don't make too many mistakes. I hope I don't offend anybody. I will certainly have tried not to do that, but we're going to go at this from the standpoint of how science might think about this, at least my view of science. But before we do that, it is time, ladies and gentlemen, to really get the answer to the riddle. I can't postpone it anymore because we don't have a video tomorrow, and I have no way of communicating the answer to you. And some of you say that I'm driving you crazy because you're up in the deck and you're running around, and what are you supposed to see and all this stuff. And for those of you who haven't done this, you avoided a lot of headaches, is the best thing that I can tell you. So let me just show you what you were supposed to see. And you see, here's the motion as you go in one direction around the ship, and the motion, and actually, what I should have really told you was walk around the entire ship and look at the ocean and walk at the starboard deck and walk at the port deck, and keep doing it until you see something different. Eventually, you will see something different. I'll try to point that out. And the other hint I wanted to give you was, did you ever go to a car wash and the car is standing absolutely still? You push the button and the brushes start to move, and all of a sudden you think you're moving, but you're really not moving? And the hints that I gave you all had to do with relativity. It's all about relativity. The first video about how fast we're really moving, is it 20 knots or is it 66,000 miles an hour? And then Lucy, in her talks, mentioned relativity, and you've heard Einstein and relativity, and so relativity is kind of an abstract until it hits you right in the face. So it's going to sort of hit you right in the face right now. So take a look at this video again. Everybody looking at it carefully? I'm going to show you something about this video. As I did say, all the hints are here in the video. Watch the sea. Appears to be still, doesn't it? Now, whoom, whoom. Seems to be shooting by you like that, right? It's still again, right? Everybody see how it's just looking still? And now, boom. Everybody see that? Can you all see how it's moving very quickly in one direction and not the other? Right? You see, everybody sees that. If you can't, go up there and look, and you'll see for yourself. Okay, so, and then I showed you this little hint here. I said, well, here's the ship moving at 20 miles an hour, 20 knots, and you're moving 2, and therefore, relative to the sea, you should be going 22 when you walk forward, which means the sea should appear to go quicker, because it's 22, you're relative to you, 22 miles an hour. And then you turn around and go the other side, the port side of the ship, and you're going backwards in the opposite direction, and the sea to you should appear to be 20 miles an hour, right? 18 miles an hour. And therefore, when you move this way, the sea should appear to be rushing by you quicker than when you turn around and move the other way. Is everybody with me so far? There's only one problem. That's not what you see. you see the opposite. When you walk forward, let's see if I one more time. When you walk forward, if we can get this to play, the sea appears to stand still. And when you walk back, the sea appears to accelerate. It defies logic. It defies physics until you remember relativity and reference frames. And that's the whole point, reference frames. Because we see what's happening here is there's more than one reference frame. What are the reference frames? There's your feet, there's your eyes, there's the ship, there's the sea, there's the railing. There's the railing. So when you go forward, the railing goes back. And what happens when you go forward as well? The sea goes back. The railing goes back and the sea goes back. They go back together. You glance over the railing and you're looking at the sea relative to the railing. And they're both going back together and the sea appears to stand still. Now you go in the other direction and the railing goes in the opposite direction to where the sea is going from the ship. And as a consequence, it's exactly the opposite. Relative to the railing, the sea accelerates even though you're going backwards. So the way you can prove this, of course, is stand in the front of the ship and the back of the ship and look out. You won't see any difference at all. Remove the railing and the whole thing disappears. Now, does that mean that that's an illusion? No. It means your reference frame has changed. Your reference frame has changed. We're not really doing 20 knots in this room. I know it's hard to believe. We're doing either 1,000 miles an hour, if you look at the rotation of the Earth, or we're doing 66,000 miles an hour, if you look at the rotation of the Earth around the sun, or even faster. So it's all relative. And here we are in our own little reference frame, completely unaware that this is what's going on in the world. But that's what it's all about. That's what Interstellar was about. So anybody who got close to that, please come to me. We're on the honor system. I'll make sure you get a copy of the books that we talked about. Okay, so with that out of the way, and continuing on the same theme, we live in a very big universe. This is from the Museum of Natural History. It's an exhibition that's very sobering. You've seen things like this before, but this is pretty spectacular. Everything you're about to see is real. The identified objects are real to the best knowledge that we have. And it's called From the Digital Universe Atlas. And if you ever go to the Museum of Natural History in New York, under the ruling of Neil deGrasse Tyson, you will see this as part of the show. Now we're going to start to proceed outward at the speed of light. So things are going to happen very fast here as we proceed towards the edge of the universe. That's 1 second in the orbit of the moon. That's our solar system. 1 hour at the speed of light. That's 1 day at the speed of light. That's 1 year. That's 70 years. That's the extent of which we've been sending signals out. Anything electronic from planet Earth, it's radio. That's 100,000 years. Just left our galaxy. That's 1,000,000 years. This is 100 million years, all the galaxies we've mapped so far. These are areas we've yet to map. That's 5 billion years. That's how old planet Earth is, roughly, a little less than that. And that's the afterglow of the Big Bang, 13.7 billion years. So, people have tried to take a look at let me see, my little twig isn't working here. How many sources, how much intelligent life might be out there with all these trillions of stars, more than grains of sand that are possibly out there? And a gentleman by the name of Frank Drake came up with the Drake equation. Back in the 60s, just shortly before a meeting, he was asked by his colleagues, can you give a wild guess about how much intelligent life might be out there? And he threw this together. And keep in mind, this is just for our solar system. And so what he did was said the number of stars in our Milky Way galaxy, and he put down 100 billion, the fraction of them with planets around them, we know there's quite a bit. We used to not think there were that many, and it's 50% the number of planets ecologically able to sustain life, and the fraction of those where life actually can evolve, and the fraction of those where intelligent life can evolve, and the fraction of those that can communicate, and the fraction of those during which communicating civilizations survived and didn't blow each other up. And if you put any numbers in here, the answer comes out to be a very, 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 very big number. That's just for our solar system, I mean, our Milky Way galaxy. And so people were saying, well, this is really indicative that there's so much life out there, we're just unable to find it or communicate with it. But in recent times, people have started to poke holes in this. They've said, we exist in a miraculous little fold that protects us from the galactic cosmic rays and the solar wind that Lucy was talking about, and where the tilt of our axis and everything about this, what's called a Goldilocks zone, everything about where we are is so miraculous and so spectacular that we might just be the only intelligent life, or life for that matter at all. And so you have this tug of war going on right now. But the answer to that, of course, is that this entire thing was for our Milky Way galaxy, and you've just seen how tiny our Milky Way galaxy is compared to everything else. So, in other words, the numbers are mind-boggling, and it's hard to get a grip on them. They're really mind-boggling. So what we do, or what I've done here, is I've tried to look at this. Are we alone? And I call this the Yom Kippur lecture, because the first time I gave this talk on a ship, it was Yom Kippur, the Day of Atonement in the Jewish religion. And I said, well, the hunt for life, meaning, and God in the universe. And so before we begin, a little bit about Yom Kippur. For those who don't know it, it's the Day of Atonement in the Jewish religion. And you are asked to atone for all of your transgressions that you might have done in the last year, and you're given, and you're completely cleansed and forgiven at the end of the day, and then you have a gigantic meal. And it comes from the El Chat prayer, the author of which is unknown. But here are some of the things that you ask forgiveness for. I'll just read them to you quickly. For the mistakes committed before you under duress, committed before you through having a hard heart, committed before you for things we blurted out with our lips. Let's see, for harsh speech, for wronging a friend, for degrading parents and teachers, for exercising power, committed before you against those who know and those who didn't know that you were committing a sin against them in the first place. How about through bribery, through denial and false promises, through negative speak, for food and drink, for being arrogant, for having a strong forehead, brazenness, right? How about for failing to accept responsibility, for jealousy, a begrudging eye, for baseless hatred, for extending the hand. God, I don't know what that means. Confusion of the heart. Oh my God, confusion of the heart. And for all the mistakes you committed before you, and you get the idea. And now you know why Jewish people are always guilty about something. They're always guilty, right? So we go on from there, and the question begs the question, who are we asking atonement from? Who are we asking atonement from? So before we try to answer that question, because this is coming at you from a scientific point of view, it's worthwhile to spend a little time talking about what science is and what science isn't. Okay, so science is a method of observing physical phenomenon and behavior and then predicting their repeatability. It's that simple. How do you do it? Okay, you do it using a set of rules. The set of rules starts with an educated guess. You've seen something, and you make an educated guess. What did you see and why did you see it? That is called a hypothesis. And from there, you go to tests to prove or disprove that guess, right? So when you do these tests, your answers have to be repeatable independently, completely outside of your world by other scientists. And they have to do it in what are called peer-reviewed journals. That means by journals that have enough academic skills to put it in perspective and repeat it. It's not baseless. They have to actually repeat what you do. And also, who does this are non-aligned judges with nothing to gain. They have no books to sell. They have no diet fads to send off. So it's always important to take a look at who are the people who are criticizing whatever's going on. What's their background? You need to go right there before you find out that you're going to trust them, just like your physicians or your doctors, anybody treating you. You need to do that. It's important. And if you forget everything else, Carl Sagan coined a phrase, which I always use, which is extraordinary claims require extraordinary evidence. If there's any possibility that it's something else, then you can't make that claim. You saw a UFO? Okay, you saw a UFO, I'll believe that. It was an alien? Well, you better be able to prove it. There's no other possible explanation. That's the only way it works. Okay, so a little bit more on it. What type of studies do you do? There are only really two kinds to prove or disprove a hypothesis. One is called cause and effect. For every action, there's a reaction. This is done in a laboratory. You do something with a chemical or physically do something, and you see a response right in front of your eyes. Action, reaction. The other one is statistical, also called circumstantial, also called epidemiological. It uses a large sample size outside a lab, an example of which is smoking causes cancer. We've never seen a cell become cancerous in a laboratory by surrounding it with cigarette smoke. That would be cause and effect. On the other hand, when you look at the data, the number of people who smoke and the number of results compared to people who don't smoke, it's very clear that smoking causes cancer. So that's the difference between a cause and effect and an epidemiological study. So after all of that, is this infallible? Is this method infallible? The answer is no. Results change. People once believed the world was flat. Some still do. We make mistakes. We're human, and experts are everywhere. So you can be fooled. It may not be perfect, but science is the best thing we have. And if you don't remember any of this at all, just remember extraordinary claims require extraordinary evidence, which, if you're looking for a higher power in the universe, you need to think about it like that. So let's just start outward from planet Earth and start looking for life and looking for some kind of evidence of spirituality. So we'll start with the moon. Here we go. And then from the moon, let me see if I have anything here that's going to play.
Did Earth have two moons? Presented by Science at NASA. Nothing stirs the soul of poets and lovers like the sight of a full moon rising on a warm autumn night. Nothing, that is, except the sight of two moons rising. If a paper published recently in the journal Nature is right, two moons once graced the night skies of Earth. The idea has not been proven. but it is drawing the serious attention of researchers. It's an intriguing idea, says David Smith of the Massachusetts Institute of Technology, and it would be a way to explain one of the great mysteries of the Earth-Moon system. The Moon is strangely asymmetrical. The Moon's near side, facing us, is dominated by vast, smooth seas of ancient hardened lava. The Moon's far side, on the other hand, is marked by mountainous highlands. Researchers have long struggled to explain why the two sides of the Moon are so different.
So I'll tell you what the theory is rather than let him go on. The theory is that when the moon was formed, there were actually two bodies formed, and one of them kind of got closer to the other one and went splat. Not a big collision, but kind of a splat, and squashed the back side and formed a different surface on the back side. Interestingly enough, Mars has the same evidence. The northern hemisphere and southern hemisphere don't look anything alike. It's called a hemispherical dichotomy. We still haven't figured that one out. But we know a lot about Mars, and in all apparent surfaces, evidence both the moon and Mars are dead places. No evidence of life that we're looking for. And then we go outwards to Jupiter. And this is recent imagery from the Juno spacecraft, which is circling Jupiter. It's quite a place. You could fit 1,300 Earths in Jupiter. There's a giant red spot that has a violent storm that's been going on over 400 years. It's a gas giant, and any kind of life as we know it certainly couldn't exist in a place like Jupiter. And then we go to some of the moons, and Europa is a very interesting place because it has a liquid water ocean, and that water remains liquid even though it's very cold because Europa slings around Jupiter, and the gravitational forces of it slinging around causes friction. Friction gets the surface temperature beneath this icy ocean so warm that it melts the ice and forms water. And you can tell this by these striations and these geographic variations on the surface that look like flexing that happen when there's an icy surface that's flexing, a liquid water beneath an icy surface that's flexing. And so there are missions being planned to go there and drill beneath the ice and go down and see if anything alive is there. And then let's proceed outward. When we get to Saturn, which is stunning. It's second in size only to Jupiter, and it has at least 60 known moons. And it's such an unbelievably gorgeous place that I have to show you this imagery that was taken when Cassini flew by Saturn, which just completed its mission a while ago. And again, the theme of music comes back and forth. It's just wonderful to, let's see, it's supposed to be music here. Yes, here we go. And here's one of the moons right over here, and you're going to see a lot of them. There's another one up there. And imagine the mission directors for Cassini at the Jet Propulsion Laboratory had to command it to fly through these rings, not knowing what they were. It took 10 years for it to get there. And this was putting it in jeopardy to get these images. And what's going on here is Cassini's actually rotating as it flies through the rings to get these images. It's rotating and aligning itself to get these amazing pictures. So I show this to some people and I say, oh, that's animation, and it's not animation. Another moon. And I love this photo. This is a picture of us from the rings. Here are the rings, and there's that little dot right there, and that's planet Earth. It would take a spacecraft 6 years to get here. Light and data or video takes 50 seconds from the time it's transmitted. That's how far away Saturn is before we receive it. And takes 50 seconds before we send a command to Cassini for Cassini to follow that command. And here's one of its moons. Speaking of looking for life. And music again. Doesn't look like a very friendly place. Looks like a rock. Looks kind of like the moon. And then you get to another one of these moons that's, at first glance, looks sort of like Lapidus, but Enceladus is different. Because when the first images came back from Enceladus, we noticed this plume coming out the South Pole and this big dent here, this big crater that happened. But this plume was especially interesting. Eruptions were coming out. And those eruptions were determined to be steam. Steam, that's water, is being boiled and it's pouring out the surface tons a second. Well, how could that be? Because it's so cold there, it's hundreds of degrees below zero. Everything should be frozen. Well, that means beneath the surface, there must also be a liquid water body. And it must be heated because it's slinging around Saturn, and that motion causing friction is heating up water, and who knows how that water got there. And it's erupting. And so now Enceladus is becoming a target of interest because if there's steam and there's water, and it's being sent into an eruption like that, you could send a spacecraft right through it and sniff for organic molecules or any kind of life. And that's a lot easier than going to Europa and digging down through meters of ice to get into the ocean. That's an easier thing to do. So now some of the interest is shifting from Europa to Enceladus for that reason. And let's go out to another moon, Titan. Titan, there's not much more I can say that she's not going to say. This is pretty...
Only moon in our solar system that has clouds and a dense atmosphere, mostly nitrogen and methane. Titan's surface remained shrouded in secrecy below the clouds until July 2004. That's when NASA's Cassini spacecraft arrived at Saturn. With its radar and infrared imaging instruments, Cassini was able to lift the veil on Titan. What scientists saw on Titan's surface astonished them. Here was a world that looked a lot like home. Its surface is complex and varied, with Earth-like features, like riverbeds, vast deserts covered in dunes, and hydrocarbon lakes. These are the first open bodies of liquid found anywhere besides Earth. On January 14th, 2005, scientists got an even closer look. The Huygens probe, built by the European Space Agency, parachuted through Titan's atmosphere, taking detailed measurements. The probe survived for several hours on the surface of Titan and returned stunning images. In spite of their apparent similarities, the differences between Earth and Titan are even more extreme. If you stood on the surface of Titan, the pressure would be like standing at the bottom of a swimming pool. The temperature is minus 289 degrees Fahrenheit, far colder than Antarctica. While rocks on Earth are made of silicates, the rocks of Titan are made of water ice. While Earth's lakes and rivers are filled with liquid water, Titans flow with liquid methane. In fact, there is so much methane on Titan that if free oxygen were also present, a single spark could cause the entire moon to erupt in flames.
So, very, very interesting, but it's not like us. No, we can't conceive of life being there. On the other hand, we couldn't conceive of life being at the bottom of our oceans next to hydrothermal vents that are close to boiling that didn't use oxygen to exist, but chemicals. And so it kind of boggles your mind what might be there, right? Let's go a little bit further out. Let's go to my favorite new place in the universe, Uranus. Some people call it Uranus, but it doesn't matter if you call it Uranus or Uranus, you're still in trouble. I think the person who named it must have had a diabolical side to them because this is always the butt of jokes when children hear about, what did you call it? In any case, despite this misunderstood pronunciation, this is the fourth largest planet in the solar system. It orbits sideways because it was smashed by a large planetary body, and its atmosphere is mostly methane, But here the pressure is 8 million times the pressure on Earth. And that causes something very interesting to happen. Carbon in the methane is compressed and compressed and compressed until it's speculated that it becomes diamonds. And so the word has it that there are diamond lakes and diamond rainstorms all over methane. Now, wouldn't that be a cool place to go? So it's got the last laugh. And then from there we go to Neptune. Neptune is 4 times the size of Earth, 13 moons, 17 times the mass of Earth, 100,000 times the pressure, 300 degrees below zero at the cloud tops and down in the center of it because of the frictional rotations, 1,300 mile-an-hour winds, 9,200 degrees at the center, not a hospitable place. And finally, we get to the ex-planet Pluto, which New Horizons visited a couple of years ago. And this looks like very interesting topography, but icy, cold, inhospitable, and barren. So speaking of life, how would you look for it? How would you go about looking for it if you suspected it from such a far distance away? So we have methods of doing that in science, and here's how we would do it. If you think about this, there's only several possibilities. One's with the naked eye. You look up there and you see evidence of it. Remember, extraordinary claims require extraordinary evidence, and our senses can be fooled. So the naked eye, or instruments here on Earth, like telescopes, spectrometers, radio telescopes, we look at the atmosphere of these places far away. Or we send robotic emissaries, and those look for it, like starting out with Voyager and Galileo, which Lucy described Voyager at length yesterday in her talk, and Galileo and Viking, Pathfinder, all of these probes that we've sent out. And let's start with the naked eye. Very fallible. So here we have, when Viking landed, it took a photograph of this, which came to be known as the face of Mars and was even the subject of some sci-fi films. Red Planet or Mission, I forget what it was. But here's the face on Mars. And of course, a lot of people ran with this and said, oh, there's a civilization there. Look what they've done. They've built the pharaoh of Egypt has gone there or something like that. Look at that face. But if you come back and look again, or you look closer, you look at a different time of year, that's what it becomes. Do not let your eyes deceive you. Wishful thinking does not work with science. Case in point, I'd like to show this from a view from one of the lobby lounges on one of the ships that I've been in the past. Look out the window and you see a flying saucer. Everybody see the flying saucer? So if you want to take this picture and tell your friends you saw a flying saucer above the Queen Mary 2, be my guest. Extraordinary claims, extraordinary evidence. Then let's take a look at instruments on Earth or near Earth, such as the Hubble, spectrometers, telescopes. And we look with these. And with these instruments, we have 2 choices. We can either look for life directly, or we can look for the signs of life. Signs of life, meaning fossils, remnants of life, or water, where life as we know it has to exist, or organic molecules, which is what we're made of. So looking back in time is instructive, because the first time we ever really tried to look for life directly was back in 1976 with the Viking missions, Viking 1 and 2. And these were brilliant experiments that were constructed by a Nobel laureate and people very well versed in how you look for life at the time. At least that's what we thought. And what they did, the basis of these search for life experiments was this. A random plot of soil on Earth would not have a single elephant. So if you're looking for big things running around, don't. But a thimbleful of soil would have millions of microbes. So Viking was based on the fact it was going to grab some soil and it was going to test it for life. So how did it test it? Well, in order to do that, it tested it based on something we all learned back in high school, which is called the respiration equation. In the reverse direction, it's called photosynthesis. But essentially, it's us. It's what's going on in our bodies all of the time, which is food. In the form, usually, everything we eat ends up as C6H12O6 or glucose. It all ends up like that before it goes into the bloodstream. Then we breathe in as oxygen. It's combined with that glucose, and it forms carbon dioxide, which we exhale, and water, which keeps our blood plasma going, and perspiration, and everything else we need water for, and heat, which is why we're all walking around at 98.6 degrees or 37 degrees centigrade, heat and energy. That is the equation of life. You go backwards and it's photosynthesis. So that was the basis of the experiments on Viking. And they had an arm that came down, it grabbed some of the soil, and it put it into a furnace, and it carried on experiments based on this. And packaging all of these experiments into a tiny little package was a brilliant exercise, a brilliant accomplishment. And they managed to do that with 3 separate experiments in Viking. And I'll show you what those look like. What their names were, because they're famous in space lore, was first a gas exchange experiment, added water, just simply added water to that soil, and looked to see if oxygen would be generated. And this one, which is called labeled release, it added a radioactive glucose, radioactive food source, and then looked to see if radioactive carbon dioxide came off, because whatever was there was breathing it, eating it, digesting it, converting it to carbon dioxide, breathing it out. And so it then looked for radioactive carbon dioxide. And the third one, called pyrolytic release, it added radioactive carbon dioxide and looked for radioactive carbon, which was being taken up and converted into food. That's the photosynthesis part. So in the beginning, all the results were positive. It was kind of unbelievable. The scientists were freaking out. It's like, oh my God. But then things started to depart very rapidly. And 2 of the experiments shortly could not be repeated with the same results. And the 2 scientists from those experiments ganged up on the third. But the interesting thing was the third experiment, labeled release, never changed. It always stayed positive. Not only did it stay positive, but what Gilbert Levin, who was the principal investigator, did was he then said, well, if you think it's chemicals, it's a chemical reaction caused by all this baking of the ozone layer because there's a thin atmosphere, here's what I'm going to do. I'm going to take a rock, I'll move a rock aside, and under the rock I'm going to take some soil that's not exposed to anything, and I'm going to see if that does it. And sure enough, it did it. Then he took another soil sample, he put it in his incubator, and it's cranking out these results. It heats it up to 320 degrees, and what happens? The results stop. So he thought he had it, and to this day, to this very day, he swears that he found life. But again, extraordinary claims require extraordinary evidence. Everybody ganged up on Gil, and they said there's a chemical explanation. It's not necessarily biological, and therefore, tough noogies, you're out of luck. And he's been fighting that battle since 1976. So NASA learned an important lesson. They said, well, we're not going to try to find life directly. That's too full of possible problems. So instead, we're going to look for the signs of life. We're going to look for fossils or water or organic signatures. And those started to show up. Here we have Allen Hills meteorite 84001, the Mars meteorite, found in 1984. And this structure here that the scientists claimed was a microfossil had been embedded inside this meteorite, which was blasted off the surface of Mars from a collision and took 13,000 years to find its way to Earth. And there are several of these meteorites that we know came from Mars, because if we look at the interior gases and other methods that we have, it's identical to what's on the surface of Mars, and it's unique. So we know this came from Mars, and this is inside of it. And they were aware of these traps, so they said instead of one logical path, they had 4 separate lines of reasoning to show that this was really a microfossil. And they were attacked as well. And there's a great book called The Mars Meteorite, and it shows you what scientists have to go through to prove that what they found is really what they say they found. And it reads like a mystery novel, and it reads like a murder mystery, because people are ganging up on these people, and they're answering back. So it's a wonderful book to read. It's called The Mars Meteorite. And so we start to look for signs of life from water, and all of a sudden we find water is in a lot more places than we thought it was. We see signs of it on the moon, in craters, deep craters. Same thing on Mercury, right next to the sun. There's evidence of water next to Mercury in crevices that never see the sun. We see it on Mars, we see it in Jupiter, we see it on Saturn, we see it in a lot of places now. And water is what we're made of. So that's encouraging. And then there's organics, looking for organic molecules. So, I mean, you have to start off. What are organics? They're molecules containing carbon and hydrogen. They are not carbon. They are not carbon monoxide. They are not carbon dioxide. They are not carbon tetrachloride. They are carbon and hydrogen. They are not stuff grown without pesticides. They are not free-range chicken and veggies, even though they're made of organic molecules. But the real definition of organics is carbon and hydrogen. And they come from anything living or dead and their end products. And we see methane, evidence of methane, on Mars. Nobody knows why. So that's the kind of thing we look for. And I'll play this very quickly because I'm in a time rush here, is that the scale of things, the scale of sizes becomes so vast when you start thinking about it. Let's quickly get here if I can. You can see Mercury and Mars, all relative sizes, and Venus, relative sizes, Earth, Neptune, Saturn, Jupiter. That's our sun. That's Sirius A, a nearby sun. That's an orange giant, and Arcturus. So the list goes on and on and on and on. And so we're really tiny, 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 like an amoeba on the surface of a pinhead. So we can't get to these places in our lifetimes. So what do we do to try to understand if anything's out there? And so we listen for signs of life. And there are sounds that we listen for. I'll give you an example of some of these sounds that we listen for to try to understand if anybody's saying something to us.
But whilst we have an overwhelmingly vivid visual understanding of space, we have no sense of what space sounds like. And indeed, most people associate space with silence. But the story of how we came to understand the universe is just as much a story of listening as it is by looking. And yet, despite this, hardly any of us have ever heard space. How many of you here could describe the sound of a single planet or star? Well, in case you've ever wondered, this is what the sun sounds like. This is the planet Jupiter.
Anyway, there's a lot of sound out there. And that prompted us to begin the SETI program, the Search for Extraterrestrial Intelligence, whereby you can help. It's a distributed network kind of program, and you can use your home computer, a screensaver. And we're listening for sounds, and there's so much coming back. You look at a spot in the sky, and you listen, and then it's recorded, and then it's put in a packet. But there's so much information, there's no one computer that can handle it, so they send these packets out to your home. And you give the screensaver, and the screensaver analyzes it and listens for signs of intelligence. And if it finds it, you may be the first person who actually discovers intelligent life in the universe. And it goes back to the SETI headquarters, and they look at it after you send it back. And so that's what the SETI program's doing, and that's remarkable. So after all of this, we have not found anything. We have not heard anything that indicates there's any other life except us. But we haven't given up. We keep listening. And by the way, that begs a question. If you did hear something, and if something was way out there, and you decided to go there, or they decided to come here, for instance, you'd probably be millions of light years away. That means by the time you got there, what you saw, what you heard, what they saw, what they heard would be long gone. Long, long gone. And that begs the question, would you really go there if that was the case? Which, of course, has led me to say there are no UFOs, flying saucers. There are no aliens that have come here because they're not taking that kind of chance if they're intelligent. Well, if they're intelligent, they're not coming here anyway. They absolutely aren't coming here. But aside from that, the issue is what you see is not what you get. So what does all of this end up saying about the meaning of life and the existence of a higher power that we call God? So you look at it scientifically, and at first blush, the evidence looks pretty bleak. We haven't found life. Every place we've looked seems desolate. The Bible makes no mention of anything beyond earth other than the heavens, which infers it was written by humans with no knowledge of the stars or the planets, not by a higher power. So the assumption of life and God then appears to be purely anecdotal. But then you remember, it's a hallmark of science to be skeptical. And you remember, extraordinary claims require extraordinary evidence. And that puts it even further down in the acceptance level of science, right? On the other hand, when the experiments of Viking failed to find life, scientists didn't give up. They changed the strategy to search for signs of life instead. Water, organics, fossils. We found methane on Mars. What does that mean? And science has learned a very important lesson coined by Wernher von Braun. This really sticks with me. Science has learned to use the word impossible with the utmost of caution. What a great phrase. Use the word impossible with the utmost of caution. I get goosebumps when I think of that, what that really means. And impossible is the calling card of a higher power, right? So let's look at the evidence of impossible, right? I'll give you some evidence of what I think is impossible, or certainly was thought to be impossible.
In a first-of-its-kind experiment, the brain activity of a monkey has been used to control the real-time walking patterns of a robot halfway around the world. Duke University researchers completed a demonstration that harnesses the brain cell activity associated with leg movement in a monkey, simulated here by computer animation, to manipulate the complex walking and standing tasks of a robot. The Duke team is working with the Computational Brain Project of the Japan Science and Technology Agency in Kyoto, Japan, to complete this research. Researchers hope this technology will one day help those with paralysis regain the ability to walk with the assistance of prosthetic devices.
So, I mean, that primate actually looked at a screen. It saw the robot in Tokyo, thousands of miles away, and it learned to move its legs in response to a treat. So it got a treat, and whenever the robot's legs moved, it learned to manipulate the robot because it was getting a banana, something like that, right? So that's kind of just the tip of the iceberg. This one I really like.
The brain is an amazing and complex organ. And while many people are fascinated by the brain, they can't really tell you that much about the properties about how the brain works because we don't teach neuroscience in schools. And one of the reasons why is that the equipment is so complex and so expensive that it's really only done at major universities and large institutions. And so in order to be able to access the brain, you really need to, dedicate your life and spend 6.5 years as a graduate student just to become a neuroscientist, to get access to these tools. And that's a shame because 1 out of 5 of us, that's 20% of the entire world, will have a neurological disorder. And there are 0 cures for these diseases. And so it seems that what we should be doing is sort of reaching back earlier in the education process and sort of teaching students about neuroscience, and so that in the future they may be thinking about possibly becoming a brain scientist. And so when I was a graduate student, my lab mate Tim Marzullo and myself decided that, what if we took this complex equipment that we have for studying the brain and made it simple enough and affordable enough that anyone, an amateur or a high school student, could learn and actually participate in the discovery of neuroscience. And so we did just that. A few years ago, we started a company called Backyard Brains, and we make DIY neuroscience equipment. And I brought some here tonight, and I want to do some demonstrations. You guys want to see some? All right. All right, so I need a volunteer. So right before, what is your name? All right, Sam. I'm going to record from your brain. Have you had this before? No. Okay. All right. I need you to stick out your arm for science. Roll up your sleeve a bit. All right. And so what I'm going to do, I'm putting electrodes on your arm, and you're probably wondering, I just said I'm going to record from your brain. What am I doing with your arm? You have about 80 billion neurons inside your brain right now. They're sending electrical messages back and forth and chemical messages. But some of your neurons right here in your motor cortex are going to send messages down when you move your arm like this. It's going to go down across your corpus callosum, down onto your spinal cord, to your lower motor neuron, out to your muscles here. And that is electrical discharge. It's going to be picked up by these electrodes right here. And we're going to be able to listen to exactly what your brain is going to be doing. So I'm going to turn this on for a second. Have you ever heard what your brain sounds like? All right, let's turn it on. So go ahead. Go ahead and squeeze your hand. All right, so what you're listening to, so this is your motor units that are happening right here. Okay, so let's take a look at it as well. So I'm going to stand over here. I'm going to open up our app here. So now I want you to squeeze. Yeah, so right here, these are the motor units that are happening from her spinal cord out to her muscle right here. And as she's doing it, you're seeing the electrical activity that's happening here. We can even click here and try to see one of them. So keep doing it really, really hard. Yeah, so now we've paused on one motor action potential that's happening right now inside of your brain. Okay. Do you guys want to see some more? All right. That's interesting, but let's get it better. Okay. I need one more volunteer. Okay. What is your name, sir? Miguel. All right. You're going to stand right here. So Miguel, when you're moving your arm like this, your brain is sending a signal down to your muscles right here. I want you to move your arm as well. All right, so your brain is going to send a signal down to your muscles. And so it turns out that there is a nerve that's right here that runs up here that innervates these 3 fingers. And it's close enough to the skin that we might be able to stimulate that. So that we can do is copy your brain signal that's going out to your hand and inject it into your hand so that your hand will move when your brain tells your hand to move. And so in a sense, she will take away your free will, and you will no longer have any control over this hand, okay? You with me? All right, so I just need to hook you up. All right, so I'm going to find your ulnar nerve, which is probably right around here. You don't know what you're signing up for when you come up and... So now I'm going to move away, and I'm going to plug it into our human-to-human interface over here. Okay, so Sam wants you to squeeze your hand again. All right, do it again. All right, perfect. So now I'm going to hook you up over here so that you get the stimulus. It's going to feel a little bit weird at first. This is going to feel like a, when you lose your free will and someone else becomes your agent, it does feel a bit strange. So I want you to relax your hand. All right, and Sam, you're with me? All right, so you're going to squeeze. I'm not going to turn it on yet, so go ahead and give it a squeeze. All right. So now, are you ready, Miguel?
Ready as I'll ever be.
Okay, so I've turned it on, so go ahead and turn your hand. Do you feel that a little bit? No. Okay, do it again.
No, a little bit.
A little bit? Okay, so relax. No, hit it again. Okay. Oh, perfect. All right, so relax. Do it again. All right, so now... All right, so right now...
Okay, I don't know if you can see where this is going, but let me take you on another journey here. We have technology that gives us big screen robotic super surgery to look inside blood vessels, and you see these amazing ability to get inside our bodies and perform these kinds of in a surgical theater like this. And then Then we have a recent experiment where people who had memory loss, they were hooked up to a encoder, and they were given questions. And they had certain right answers and wrong answers to these questions. And these were encoded, and then they were fed back into the person as a code being fed back into their brain. And the second time they were asked a set of questions, their right answers improved by 35%. So all this stuff is going on, and where it's really ending up is something like this.
Hi. I'm going to ask you to raise your arms and wave back just the way I am, kind of a royal wave. You can mimic what you can see. You can program the hundreds of muscles in your arm. Soon, you'll be able to look inside your brain and program, control the hundreds of brain areas that you see there. I'm going to tell you about that technology. People have wanted to look inside the human mind, the human brain, for thousands of years. Well, coming out of the research labs just now for our generation is the possibility to do that. People envision this as being very difficult. You had to take a spaceship, shrink it down, inject it into the bloodstream. It was terribly dangerous. You could be attacked by white blood cells in the arteries. But now we have a real technology to do this. We're going to fly into my colleague Peter's brain. We're going to do it non-invasively using MRI. We don't have to inject anything. We don't need radiation. We will be able to fly into the anatomy of Peter's brain, literally fly into his body, but more importantly, we can look at his mind. When Peter moves his arm, that yellow spot you see there is the interface to the functioning of Peter's mind taking place. Now, you've seen before that with electrodes you can control robotic arms, that brain imaging and scanners can show you the insides of brains. What's new is that that process has typically taken days or months of analysis. We've collapsed that through technology to milliseconds, and that allows us to let Peter look at his brain in real time as he's inside the scanner. He can look at these 65,000 points of activation per second. If he can see this pattern in his own brain, he can learn how to control it. There have been 3 ways to try to impact the brain: the therapist's couch, pills, and the knife. This is a 4th alternative that you are soon going to have. We all know that as we form thoughts, they form deep channels in our minds and in our brains. Chronic pain is an example. If you burn yourself, you pull your hand away. But if you're still in pain in 6 months or 6 years' time, it's because these circuits are producing pain that's no longer helping you. If we can look at the activation in the brain that's producing the pain, we can form 3D models and watch in real time the brain process information, and then we can select the areas that produce the pain. So put your arms back up and flex your bicep. Now imagine that you will soon be able to look inside your brain and select brain areas to do that same thing. What you're seeing here is we've selected the pathways in the brain of a chronic pain patient.
So what he's saying is that we are at the cusp of being able to control depression, neurological diseases, pain. We're at the cusp of being able to bypass breaks in our spinal cord and have a signal bypass the break and move our limbs. We're at the cusp of doing miraculous things. Miraculous. And so, in short, the kind of miracles being accomplished in the name of science can only be explained by a higher power that permeates every cell of our body, a force that makes the impossible possible. Whatever name you give it, there's only one appropriate response, and that response is to be grateful, gratefulness. So I'm going to close with this video, which I'm sure the captain is going to interrupt in exactly 1 minute. So we have a choice. We can either sit here and make his miraculous announcement that we suddenly lost an hour and we're in a different time zone, or I can play it right now and you can kind of try to tune him out. So raise your hands. Should we go now or should we wait? Go now? Go now. Okay, here we go.
You think this is just another day in your life? It's not just another day. It's the one day that is given to you today. It's given to you. It's a gift. It's the only gift that you have right now, and the only appropriate response is gratefulness. If you do nothing else but to cultivate that response to the great gift that this unique day is, if you learn to respond as if it were the first day in your life and the very last day, then you will have spent this day very well. Begin by opening your eyes and be surprised that you have eyes you can open. That incredible array of colors that is constantly offered to us for pure enjoyment. Look at the sky. We so rarely look at the sky. We so rarely note how different it is from moment to moment with clouds coming and going. We just think of the weather, and even of the weather we don't think of all the many nuances of weather. We just think of good weather and bad weather. This day, right now, is unique weather. Maybe a kind that will never exactly in that form come again. The formation of clouds in the sky will never be the same that is right now. Open your eyes, look at that. Look at the faces of people whom you meet. Each one has an incredible story behind their face. A story that you could never fully fathom. Not only their own story, but the story of their ancestors. We all go back so far. And in this present moment, on this day, all the people you meet, all that life from generations and from so many places all over the world flows together and meets you here like a life-giving water if you only open your heart and drink. Open your heart to the incredible gifts that civilization gives to us.
It's only got another 2 minutes to go, folks.
Electric light.
Hold on a bit.
Turn a faucet and there's warm water and cold water and drinkable water. It's a gift that millions and millions in the world will never experience. So these are just a few of an enormous number of gifts to which we can open your heart. And so I wish you that you will open your heart to all these blessings and let them flow through you. That everyone whom you will meet on this day will be blessed by you. Just by your eyes, by your smile, by your touch, just by your presence. Let the gratefulness overflow into blessing all around you. And then it will really be a good day.
Thank you for coming. It's been a pleasure to meet some of you and exchange ideas and give you a little bit of perspective. And we'll see you tomorrow at the panel discussion where you can ask any kind of question you want. And again, thank you for helping me to have the energy to do all of this and the passion. Thank you.